Alright, so going with the lecture. What have we done to work ourselves? Where are we at right now in solids? Well, we've seen that we take a beam and we put arbitrary loadings on it. Maybe some load here. We can take this and we can find the moment equation as a function of x and the shear equation as a function of x. Right? That's what we've done up until last week. Last week, we derived the equation for bending stress. And we saw that bending stress is given by my over I. It was important to remember that when we derived that equation, this was just a form of the fact that stress is equal to E epsilon, or the strain, which is Hooke's law. But we noticed that for any bending moment, the strain seen in a beam is proportional to the radius of curvature. So we need to remember that the strain was seen to be negative y over rho. Well, that was the radius of curvature, and we were able to prove that 1 over rho was equal to m over EI. This is a big equation for what we're going to be looking at today. So let's make sure that we remember when Dr. Gamal proved that to us. Okay, so with that in mind, I'm going to have to give you a quick refresher from your Calc 4 class. In Calculus 4, we were able to see that for any function y is equal to f of x, we could find the radius of curvature of that function. And the radius of curvature, if we have y and x, let's say we just have some random function, would be a circle that would have the same tangent as the derivative at this point. So if we had a circle with this radius, that would be the radius of curvature at that particular x. In calculus, your professor proved that the radius as a function of x was equal to d squared f over dx squared, all divided by 1 plus df dx squared to the 3 halves. Okay, that's just a quick review of something that we saw in Calc 4, and we're going to need that as we continue on today. So, if we're looking at a beam, and we're loading a beam in a particular manner, that beam is going to deflect, right? That beam is going to bend. So if I go here, get another color, it'll probably help out. So if we have some coordinate axis, and we have some beam that's supported on that coordinate axis, if we apply loading to that beam's not going to continue to stay straight. It'll actually deflect due to that loading, right? So we want to be able to predict how much a beam can deflect, because that's an important thing to be able to do if you're looking at structures. So if we want to be able to figure out how much that beam deflects, we can use this relationship from calculus and this equation that we derived last week to be able to predict that deflection. In solid mechanics, we often use lowercase v as a deflection. It's confusing because uppercase v is the shear. So it can be kind of confusing. Make sure you keep your uppercase, lowercase straight, because v kind of looks the same either way. But if we call v the deflection and we call this axis x, we can see that 1 over the radius of deflection from that equation that we saw earlier is going to be del squared v del x squared over 1 plus del v del x squared, all to the 3 halves. Now, if we equate 1 over the radius of curvature to what we used to prove bending stress last week, we also see that that's all equal to m over EI. So now we can predict what the deflection of the beam will be at any x location due to the moments that we can find at that location in x. So depending on what that moment is, it'll give you a greater radius of curvature and a greater deflection for a larger moment. So, in solid mechanics, We often like to simplify these equations because this is really complicated. In fact, that's too complicated to solve in most cases. So we want to make some assumptions that will make that a little bit easier to solve. And we always look at small deflections when we're looking at solid mechanics. And so if we're looking at small deflections, that means that the change in the deflection, or the change in the slope, is going to be very small. What we're trying to say for small deflections is we get to say that dv dx is small, which means that dv dx squared is approximately 0. And if we do that, we get to just delete the entire bottom of that equation, and it makes things a lot easier for us. So this equation greatly simplifies down to the fact that now we can relate the moment to the deflection by just 1 second derivative. So now we can see that the moment at a given location in x is equal to b squared v dx squared. And that's our basic equation that we're going to look at for at least the first half of class today. So this is a very important relationship in proving how beams will act when given to a specific loading. Because we can go look at an arbitrary loading, find what the internal moment in that beam is as a function of x. And due to that, we can find the deflection at every point in that beam. So this is often simplified, and an easier way to write it as m is equal to e I v double prime. You'll remember from Deflection that a lot of times you'll do a prime as a derivative with respect to x, and a dot as a derivative with respect to time. So that's just an easier way to write it, and we'll use that for, the remainder of this class or this lecture. So if v is the deflection, what can we say about v prime or v double prime? Well, v double prime is directly proportional to the moment seen in the beam. But if we want to look at v prime is going to be the slope of the beam or the deflection. So if you think of it as kind of, if we have a cantilever beam, that's some beam, when we put some load on it, that'll deflect, something like that. So if we go out and we look at the end of this beam right here, we have this right here, and that theta is going to be what our value of our slope is at that point. So if you're trying to think of a physical meaning for what v prime or v double prime means, so v is the deflection, v prime is going to be the rotation of the beam, or the level of twist of the beam, or something like that. Sometimes we'll call that the rotation. We might just call that theta of x. So based on that, let's try and look at how we would solve this equation. So if you remember, equations like this from Deflection, that's a differential equation. It's a second. We have a second derivative here, so that means that we need 2 boundary conditions to ever solve that condition. So if we're going to apply boundary conditions to an actual beam, how would we do that? And that really depends on the situation, what you're looking at. So if we're going to try to find boundary conditions for this equation, that's all due to how the problem is set up. So let's just give some examples. If we have a beam with pinned ends, what is going to be the deflection at the pinned location? It's going to be 0. So our boundary conditions on this particular case is going to be that x is equal to 0, the deflection is equal to 0. At x is equal to L, the deflection is going to be equal to L. Does that make sense? Everyone follow me? That's not always true for any locations. If we had a additional pin joint there at the middle, we'd also have at x is equal to L over 2, the deflection would be equal to 0. So that's an example of a boundary condition, because from this equation, if we're looking for the actual deflection, or the deflection of the beam, we can see that E I V is going to be equal to the double integral of the moment equation that we solved plus plus some constant of x plus another constant. So we need to solve for a constant C1 and C2 when we do that using boundary conditions.
Real quick, you have deflection is equal to L. Are those both zeros?
Oh, I'm sorry. Yeah, these are both zeros. Thanks. Yeah, those are both zeros that are at our boundary conditions. Another example of a boundary condition. Let's say we have a cantilever beam. What is going to be the deflection at the wall? It's going to be 0. But just like, and also at a cantilever beam, you can't rotate where you're connected to that wall. So our other boundary condition in this case is going to be that x equal to 0, v prime is equal to 0. Because v prime is our rotation. We're going to have 0 rotation here at the wall. So those are examples of how you look at boundary conditions. There's also another important style of boundary conditions that you have to assume to solve more complex loading problems. So keep that right where it is. So in a case like this, where we have complex loading, we have a point load, or we have a distributed load that doesn't go all the way across the beam. You remember that when we had to find our moment equation for this beam, you actually have to do it piecewise. You have a function that's valid for section 1, a function that's valid for section 2, and a function that's valid for section 3. So our last boundary condition that we want to consider is that if we have some beam that has a complex loading system like that, we know that where we have two sections, so if I have this be x1, call that x2, our deflection needs to be continuous across that transition. So we know that the deflection, so we're going to have three equations just like we would for the moment, because if we found the moment as a function of x, we'd have three equations. We can integrate that using that equation right there, and we get three different equations for the deflection of the beam. So we know that if we have a deflection equation here called V1, V2, and V3, we know that V1 is going to be equal to V2 at x1 equal to x, or x equal to x1. And we know that V2 is going to be equal to V3 at x is equal to x2. Because you can't have any sharp breaks in deflection because it's a beam, it's a solid, it's all continuous material. So those are the main styles of boundary conditions that you're going to have to use when you solve this equation. And every time you solve this equation, you will have two constants that you need to solve for. Now, a lot of times they'll turn out to be 0 if you look at it in a clever way. They might simplify a little bit easier than that, but you're always going to have those two constants that you need to solve for. So let's work an example that we can try and illustrate how this is important. So, clear the board. Okay. So let's say we have a cantilever beam of length L with a point load acting on the tip of that beam. What is the deflection in that beam going to look like? Well, the first thing we got to do is we got to find our reaction forces, because we're doing the same thing that we always do, trying to find the moment equation. So if we look at just this beam, we're going to have a reaction force of P at the wall. And we're going to have a moment with the magnitude of PL at the wall, just to make sure that the rotation around, if I make some of my rotations around the point of the wall, it has to be equal to 0. So with those reaction forces, we can then go ahead and solve for our moment equation. So when you solve for your moment equation, you have to make a cut, right? First thing you always do is you make a cut. We have some moment, we have P, and we have PL. So based off that, if I sum my moments, moment plus PL, because they're both in the same direction, assuming this is a positive moment, minus P times X is equal to 0. Because this distance right here is our X distance. So, based off that, my moment as a function of X is going to be equal to P times X minus L. Now we remember from what we just saw earlier in this class that we can say that M is equal to E I V double prime, which means that E I V double prime is going to be equal to P times X minus L. So based on that, we can now solve for the deflection at every X location along the beam by integrating this equation twice. So, if we integrate it the first time, we can see that E I V prime is going to be equal to, if we integrate that, we get P times the integral of X minus L dx, which is going to be equal to, let's see, P times X squared over 2 minus LX plus C1. So, we go ahead and we start applying boundary conditions. If we apply them now, we don't have to worry about it later. So, if we can go ahead and get rid of C1 or do something with C1, when we integrate it again to get our deflection equation, we don't have to worry about it just being an arbitrary constant. We know that for cantilever beams, that at X is equal to 0, the displacement is equal to 0. So at X is equal to 0, this term goes to 0, this term must be equal to 0, so we know that C1 has got to be equal to 0. So now we know what the rotation is at every X location for the cantilever beam. We can go ahead and we can integrate that one more time to figure out what the deflection is going to be at every X location. And we'll find that EIV is going to be equal to P times the integral of X squared over 2 minus LX dx. And we end up seeing that that's going to be equal to P times X cubed over 6 minus LX squared over 2 plus C2. And that is going to be my basic deflection equation. So, if I look at that, I got to go ahead and apply boundary conditions again. So, looking at that, I know that the deflection at X is equal to 0 has got to be equal to 0 because it's cantilever beam. So, this term goes to 0 and X is equal to 0. This term is supposed to be equal to 0, so we see that C2 also turns into 0. And we get to lose that particular deflection equation. So, that means that our total deflection is going to be equal to P after some factoring times X over 6 minus L over 2. That's kind of a great mathematical exercise to be able to prove that, but really what does that tell us? So let's plug some numbers in. Let's say that L is equal to 1 meter. We have P is going to be equal to 10 kilonewtons. Let's say that E is steel, so about 200 gigapascals. And let's say that I is equal to 800 centimeters to the fourth. That's like a 7 centimeter by 7 centimeter cross section of a beam. So that's realistic numbers that maybe you would see if you were putting a load on a beam. If we go ahead and we plug that in, we want to find what the deflection is at the tip. So let's go see what the maximum deflection is, which will be found at the tip. We just plug all those numbers directly into that equation, and we would see that V is going to be equal to P, which is 10 times 10 to the third newtons, times X, which is 1 cubed, over E, which is 200 times 10 to the 9, times I, which we said 800 centimeters to the fourth, so 800 times 1 over 100 to the fourth, multiplied by, let's see, x over 6, which is just going to end up being, okay, so if we go ahead and plug in x is equal to L in this location, in this situation, I'll just go ahead and do it, it's not a problem. So x is going to be 1 over 6 minus 1 over 2. So if you run that through on your calculator, you're going to find that v is equal to negative, this is, oh, so I think I definitely, no I didn't, I'm good. So v is going to equal negative 0.00208 meters, which is going to be equal to negative 2.08 millimeters. And that's going to be our maximum deflection that we see in this case. See, but we generalized it down using this equation, and this holds true no matter what the geometry or the size of the beam is. So that's always true for a cantilever beam with a point deflection on the tip. And then you can always go through and you can plug your actual values from your problem into the equation and get the actual deflection. So let's go ahead and work another example where we needed to use some of this more complex boundary conditions. Because these are the ones that are time consuming, and these are the ones that you don't want to mess around with on a test. You want to be able to just go ahead and work those out as fast as you can. So, let's say we have a beam. I should probably. We have a beam, and it has 2 pin joints, 2 pins on it, and on this end sticking out past the second pin, we have a distributed load that goes across that beam with a value of W. That'll be your force per unit length value, as you've seen a bunch of times. We'll say that these are equal lengths. This has a value L, this has a value L. And we know that because these are pin joints, they're going to have, I call this A, B, C. We're going to have an A reaction force and a B reaction force. So the first thing we need to do is we need to solve the statics problems, and we need to make sure that we solve for our A and our B values correctly. So the first thing I can do is I can sum my moments around B to figure out what A is supposed to be. So if I sum my moments around B to 0, I know that WL acting at a distance of L over 2 is going to be equal to, actually does it, if we're going to, things that all rotate the same direction. So plus A times L is going to be equal to 0. So I know that my assumed direction for A in this location, or at this point, is wrong. And I can prove that A is equal to negative WL over 2, or that it actually points down. Then, by summing my forces in the y direction to 0, I can find that WL plus, or so that's going down, A sub y is going in down direction 2, so this is going to be down, it's going to be plus WL over 2, it's going to be equal to what's in the up direction, which is B. So B is going to have a value of 3 WL over 2. Okay, so that's what we need, and that's what we need. Okay, so in this case, how many different sections do I have to look at? I have to look at 2 based on what my loading condition is and where my pins are placed. So that means I'm going to have 2 moment equations that I got to solve, which which means I'm going to have two deflection equations, which I need to apply boundary conditions to solve the deflection of the total beam. So the first thing we need to do is we need to solve for the moment equations of both sections, sections 1 and section 2. So I can do that by making a cut in the first case before we reach the second pin joint. So we have some beam, it's got a negative A force equal to WL over 2, and we have some moment that's acting in this location. So if I go ahead and I sum my moments around the cut, I can find that M1 is going to be equal to negative WLX over 2, because this is my distance x. So there's my first moment equation. Then I need to go through and I need to solve for my second section. So in this case we have an A force, that's WL over 2. We have a B force acting at the center of the beam, which we said was 3WL over 2. And now we get to deal with the portion of the distributed load acting on that beam. So using a similar argument, we're going to go ahead and we're going to find the moment equation, the second portion of the beam. So I can go ahead and I can sum my moments around the cut, and I can find that if I say things that go this way are M2 plus WL2 or WLX over 2, and things are going to be equal, I guess we have this one working as well, plus, let's see, 3, no, that's the wrong one. So plus W times X minus L is going to be the resultant force due to this distributed load. And that's going to be acting at a distance of X minus L over 2. Those got to be equal to things that we're going to spin it this way, which is going to be just 3WL over 2 acting at a distance of X minus L. So from this, we can see that our moment equation, by just solving for M2 and rearranging our terms, so that our M2 is going to be equal to 3WL over 2 times X minus 3WL squared over 2 minus WL over 2 times X minus W over 2 all times X squared minus 2XL plus L squared. So that's a much more complex moment equation that we're going to have to integrate now and apply boundary conditions to. You always kind of want to multiply things out as best you can, because when you integrate it, you're just pretty much running polynomials, and it makes it a lot easier if you can look at each term individually.
Did you say all of that times x squared minus 2x?
Yeah, so this is really here. So that's right out of space. Okay, so if we go ahead and now we try and find what our deflection is for the first portion of the beam. We just do that by integrating the first moment equation right, or our first moment equation, and then we can apply our boundary conditions. This one's a lot easier to integrate than the second one. And this is our second equation. So our first moment equation is we can see that we can say that EIV double prime is equal to negative WLX over 2. So EIV prime is going to be negative WLX squared squared over 4 plus some constant. We integrate that one more time. And we see that it's negative WLX cubed over 12 plus C1X plus C2. We have to include our constant of integration here. That's not a prime. So we can do the same thing with our second moment equation to find the deflection of the second portion of the beam. We see that, so this I'm going to call the first equation, I'll call it V1. I can see that EI V2 double prime is going to be equal to M2, which, if I go through and simplify this, so we need to integrate this equation, which I said, so if you multiply this out, some of our terms go away, and it actually simplifies even further. So our M2 ends up being negative WX squared over 2 plus 2WLX minus 2WL squared. That's when we multiply this through this. It's actually going to clear up some terms here. So that is equal to what we saw before, which is negative WX squared over 2 plus 2WLX minus 2WL squared. So by integrating that one time, the EI V2 prime is going to be equal to negative WX cubed over 6 plus WLX squared minus 2WL squared x plus a constant of integration. And then we have, that's confusing, so I already have a C1, that should be a C3. And then we have our deflection for the second portion of the beam is going to be given by negative WX to the 4th over 24 plus WLX cubed over 3 minus WL squared x squared plus C3x plus C4. And now we have to apply our more complicated boundary conditions to find what C1, C2, C3, and C4 are. So, our first boundary condition we want to apply is we know that the deflection at x is equal to 0 is 0, and that's going to apply directly to our V1 equation, our deflection of the first half of the beam. So, when x is equal to 0, this term is 0, this term is 0, so we know that C2 goes away. Now we know that V1 is also, the deflection is also 0 here at x is equal to L, which is where our B reaction force is occurring. So we can then apply that boundary condition to our simplified equation. We see that 0 is going to be equal to negative WL to the 4th, so we're saying L is equal to 4 over 12 plus C1 times L, which means that C1 is equal to WL cubed over 12. So, our next boundary condition we want to apply is because this beam is continuous, we know that the slope at this support is going to be the same for both sides of the equation. So I know that V prime of 1 at x is equal to L is going to be equal to V prime of 2 at x is equal to L. So I can apply that boundary condition, and we know what C1 is now. So I know that negative WL cubed over 4 plus WL cubed over 4, which was, or WL cubed over 12, which is C1. That's our first half of the equation. It's going to be equal to this equation, which will be negative WL cubed over 6 plus WL cubed minus 2WL cubed plus C3. So I can then say that C3 is going to be in WL cubed. I can factor out of everything. I can subtract these 3 terms from this term, so I have a negative 1/4 plus a 1/12 plus a 1/6 minus a 1 plus a 2. So that gets me that C3 is going to be equal to WL cubed. I can see that because this is going to sum to 1, which means this goes to 0. Okay, so we have 3 of our constants. We need to go ahead and find the last one. And I don't really want to erase the problem statement. And we can find what C4 is by recognizing that V1 and V2 are both 0 at x is equal to L. So V2, just like V1 was 0 at x was 0, we know that our second deflection has got to be 0 at this pin joint as well. So we know that 0 is going to be equal to negative WL to the 4th over 24. I'm pulling all this from this equation right here. Plus WL to the 4th over 3 minus WL to the 4th plus WL to the 4th plus C4. From that, we can find that C4 is got to be equal to negative 7 WL to the 4th over 24. So now that we solved all of our equations, we can then write what the deflection.
Where did we solve what C2 was?
Huh?
Where did we solve what C2 was?
We saw that what C2 was 0 at the very beginning because, I guess I already erased it. We saw that, we recognized that the deflection at 0 is equal to 0 for V1. So when I solved, there, that's where I solved it right here. So here was my V1 equation. I plug in x equal to 0. That term went away. That term is equal to 0, so C2 had to be equal to 0. So in this case, now that we're done solving all these equations, we can see that V1 is going to be equal to WLX over 24 EI times L squared minus X squared. This is after applying that C2 was 0 and that C1 was WL cubed over 12 and did some factoring. This is valid for 0 is less than or equal to X is less than or equal to L. And we saw we could find by plugging in what we got for our other 2 integration constants that this is going to be equal to W over EI times negative X to the 4th over 24 plus LX cubed over 3 minus L squared X squared plus L cubed X minus our last integration constant that I just erased, or there, minus 7L to the 4th over 24. And that's valid for L is less than or equal to X is less than or equal to 2L. So you can see this can be really tedious. And so, just for studying, you're going to probably solve one of these on the homework. I would not expect to see one of these on the test, just if you're trying to think about purely trying to make an A in the class. So you can see that from this loading, we can find out what the deflection is at every X location along the beam, and then by substituting what our actual physical values are in for L, E, I, and W, we can actually find the deflection at any given point. We can then predict what, we can then design to make sure that we're okay with that deflection, or that we are designed to be able to withstand that. We have proper clearances in our beam or truss system. So, does anyone have any questions up to this point in time? Everyone following me? Fine? No issues? Because we're going to take what we just learned, that we can integrate the moment equation twice with the deflection. We can expand upon that and recall from what we saw doing moment and shear diagrams, and we can actually integrate the loading equation on a beam 4 times to get the deflection at every point in the beam. And while not always practical, it's something I guess we felt was important to include in the course. So now let's look at another situation. Back when we were looking at moment and shear diagrams, if we have a beam, what time's this class out? Now? Oh, sorry.
5:45.
What time? We have half an hour still? Okay, so if we have some loading equation that we don't know what it is, or we know what it is, but it's not something that's easy to examine. We have some loading function w of x. We can do the same sort of thing if we recall from when we were doing moment and shear diagrams that negative w of x was equal to our derivative of our shear, which is a capital V, dx. And we can also recall that our shear was equal to the derivative of the moment equation. And if we put all this together, we can see that the moment, if we take the derivative of it twice, is going to be equal to the negative of the loading function. Now, from this, we know that dx of EI, let's see. So, this was our equation that we saw before, just this. We have that the moment function is equal to the second derivative of the deflection times E times I. We can take the derivative of this entire equation, and that's going to give us that the shear function is going to be equal to EI, the triple derivative of our deflection equation. We can then take the derivative of both sides of this equation, and we'll get that the negative of the loading function is going to be equal to E times I times the 4th derivative of our deflection equation. So now, given we have a function that describes the loading, we can find the deflection at any x location along the beam. So, to kind of summarize, we have the loading function is going to be equal to EIV 1, 2, 3, 4. We have that the shear function is going to be the 3rd derivative of the deflection. And we have that the moment equation is going to be equal to the 2nd derivative of the deflection, and we have that the rotation angle is going to be equal to just the derivative of the deflection. So those are, I guess, every step from deflection all the way down to loading that if you wanted to find for any given particular structure. So based on this, let's work an example on which we integrate a loading function. Let's say we have a simply supported beam that has a variable load that goes from 1 kilonewton meter to 2 kilonewton meters linearly. So the first thing that we have to do is if we're given this problem, we need to figure out what that loading function is. We know it increases from 1 to 2 over, let's say that this length is 2 meters. Now we're going to need 2. So based on this, we know that it increases from 1 to 2 over distance of 2 meters. So my rise over my run is going to be 1 over 2 in this case, and it starts at a constant value of 1. So our loading function is going to be equal to x over 2 plus 1. That is the loading that we see on the beam. So I can integrate this to get my shear function. My shear function, which is equal to negative integral of that, then equal to negative x squared over 4 plus x. Oh, that's I already integrated it. So x squared over 4 plus x plus c1. I can integrate that again to get my moment equation. I get that my moment equation is going to be negative x cubed over 12 plus x squared over 2 plus c1x plus c2. I can then apply boundary conditions that we remembered from doing moment and shear diagrams. And what do we know about the moments at our endpoints on our pin beams? So pin beams can't exert a moment on the beam, so our internal moment goes to 0 at these locations. So I can apply my boundary conditions at x is equal to 0. I know that the moment is equal to 0. That makes C2 go away. And when I know that m at x is equal to 2, going to be equal to 0. And I can plug that in. That's going to be negative 2 cubed is 8 over 12 minus 4 over 2 plus C1 equals 2. I can find that C1 is equal to 4/3. Okay, so let's just write that out again. So if I go ahead and I substitute my negative sign through, I know that my moment equation now becomes negative x cubed over 12 minus x squared over 2 plus 4/3 x. I can then integrate that one time to find out what, or that's, remember from our moment equation, that's equal to EI, the second derivative of the deflection. So I can now integrate that to figure out what my rotation angle equation is. So my rotation angle equation becomes negative x to the 4th over 48 minus x cubed over 6 plus 2x squared over 3 plus C3. I can then keep going and integrate it one more time. In my deflection equation, I see that my deflection equation is given by negative x to the 5th over 240 minus x to the 4th over 24 plus, let's see, 2x cubed over 9 plus c3x plus c4. So you can see, even for a very, very simple loading such as this particular method for finding the deflection of the beam can be quite time-consuming and pretty tedious. So we need to apply some boundary conditions to figure out what our C3 and our C4 is. Well, we know that the deflection is equal to, at x is equal to 0, is equal to 0. And that will give us, if I plug in x is equal to 0 this equation, all of these terms go to 0, that term goes to 0, we get that C4 is equal to 0. If I apply my v at x is equal to 2 is equal to 0. I didn't plug all that, so this equation goes away, or this constant goes away, and I can plug 2 in for all these values. I get that negative 32 over 240 minus 16 over 24 plus 16 over 9 plus 2c3 is equal to 0. I can solve that, and I get that c3 is equal to negative 22 over 45. So, that's all well and good. What does that end up getting us for our final deflection equation? So our deflection as a function of x is going to be equal to negative 1 over EI times negative x to the 5th over 240 minus x to the 4th over 24 plus 2x cubed over 9 minus 22x over 45. So, if I go ahead and I say that, let's just say that EI was given to be 200, that the units of that are going to be kilonewton per meter squared, or kilonewton meter squared. I can find out that the deflection at the midpoint of the beam, so at x is equal to 1, would be something like negative 1.563 millimeters. And this is, we need to make sure whenever we do these equations, we need to make sure we check and we have small deflections. These are not valid for large deflections. Once you leave the linear elastic portion of the material properties, these equations are not valid. These are only valid for very small deflections.
How small is very small?
Use your engineering expertise on that one. It should be several orders of magnitude smaller than the length of the beam. And if you look at very thin beams that can deform very, very much and then come back again, these are not quite like for sheet metal. This is not valid for sheet metal. It's valid for beams, I-beams, wooden structures, things that are in the linear elastic material property range. Alright, are there any questions? None at all? We're not going to roll. Y'all get out of here.